All right, once again, Fort Collins, you're listening to 90.5 KCSU FM, and you're listening to Science CSU. I'm Rachel Mason.
And I'm Tyler Stupp.
And today we're actually sitting in studio with Adam Allevato. He is a honor student here at CSU working on his thesis currently, and he's going to talk to us a little bit about that. So welcome, Adam. Good to have you here.
Thank you very much.
So why don't we just start off with a little bit of background about yourself?
Sure. Well, I'm originally from Southern California, and we moved to Colorado about 6 years ago and started coming to CSU. I'm a senior here, graduating in May. I'm studying mechanical engineering, and I just really love all sorts of technology, science, engineering, math, you name it. If it's nerdy, I love it. So.
Nice. And why pick CSU in particular? Why Colorado?
Well, I wanted to keep in-state tuition because I was already living in Colorado at the time, but CSU really made me feel like they wanted me to be here, whereas other schools I talked to, they said, congratulations, you're enrolled, and then I never heard back from them. So CSU really kind of went the extra mile to make me want to be here.
And what got you interested in mechanical engineering?
I just really love to build things. I would play with Legos literally all day when I was little, so this just kind of seemed like a logical conclusion. And, I was always good at physics. Physics was my favorite subject in high school, and so between those two things, and I'd already picked up some programming, I definitely wanted to do engineering, and I like working with my hands, so mechanical was great.
So why don't you give us kind of an overview or a summary of the project that you're currently doing?
Sure. So our project is for the United States Air Force Research Laboratory, and they run a competition, a student design competition every year to try to generate new ideas to solve problems that they have out in the field. So this year what they're trying to do is solve the problem that when you have parajumpers that jump out of a plane, they often have to go into an environment where there are maybe vehicles that have been flipped over, maybe by a bomb, or there's a building that's been collapsed, maybe it's a rescue mission essentially. There's something that's trapped under a really heavy object, and you need to get that object lifted or out of the way so that you can get whatever's underneath. So maybe that's a person, maybe that's equipment. The main goal is to just lift that heavy object. So our student design team has to build a device that will actually do that while also being very light and small so it can fit in your backpack when you jump out of an airplane.
And when you are given a task to accomplish like that, where do you start in the design process? Is there like you always start at this point and you just kind of like branch out, or?
That's a really good question, especially with this project. The actual requirements are so strict that we almost didn't know where to start, because the device has to weigh less than 30 pounds, has to fit in a 1 foot by 1 foot by 6 inch space, and has to lift 45,000 pounds. So the constraints were phenomenal, and we basically sat down the first day and our team looked at each other and we just said, how on earth are we going to do this? And so what you really have to do is you have to understand the problem as well as you can. I think that's always the first step for design problems like this. You understand the problem, you understand what other people have tried to do, and then once you've done that, you have a better understanding of how you can actually go about solving the problem. Then you go through as much brainstorming as you can. We had everything from robots that crawled underneath the vehicle to lift it, to airbags, to you name it. We came up with it and threw it up on a whiteboard, and then we just tried to whittle it down to what we thought were the best designs and went from there.
What is the current method? How well does that work?
So the current method is essentially an airbag. I mentioned we looked at airbags, but that's essentially what they use already. So firefighters use that a lot, and the Air Force does too. So you put it underneath, and it's really flat and really small, and then you have a giant tank of compressed air, and you just transfer the compressed air from that tank into your bag. It fills up, and then it lifts the load. So it really does work a lot like an airbag. But unfortunately, those are really big and heavy. They have to carry them around in 2 large duffel bags, and they're only capable of lifting about half the weight, about 22,000 pounds. So it's really not what the Air Force is looking for. That no one takes those into the field. They're too big.
So you said that no one takes them into the field. How do they get this equipment and these people out of these situations if they're too heavy? Is there they just kind of leave it?
Like in a lot of cases, I think their hands are kind of tied. Like if they know they actually are going down and they're going to need to lift something, they'll do what they need to do to get equipment down there to actually lift a heavy object. But often you just don't even know what you're going into, so you want to have that device that you can just throw in your backpack just in case. But for example, if you're in a vehicle and it gets flipped over by a roadside bomb, basically you just got to sit tight there and hope that, insurgents don't find you for the next 3 hours until they can bring along a vehicle that actually has a crane on it that'll essentially flip your vehicle over and let you out. So, yeah, it's not a good situation to be in if they don't have a way to let you out.
So, clunky airbags was the first kind of, air quotes, working method.
Right.
What did you do to kind of improve on that idea?
This competition's a little interesting at CSU in particular because there are actually 2 teams that are doing the exact same competition, and we're competing against each other, and then the one that does the best will go on to compete in the national competition. So the other team actually did just take the airbag idea, run with it, and improve it. So they're using stronger, lighter materials. They're trying to use a chemical reaction. They're going to either combust sodium azide or look at some experimental chemicals that come out of the Los Alamos National Lab to try to generate enough gas to actually inflate those airbags. But we figure we're mechanical engineers, and we're just going to take a whole different approach, and we're going to do something mechanical. So the best way I can describe the way our device works is if you imagine a tape measure is all coiled up inside the actual little tape measure, but as you extend it, it can kind of stay rigid because it has a little curve to it, and so it has some rigidity about its axis. So we're essentially taking the idea and magnifying it a whole bunch so that essentially, if you imagine the tape measure, that tape measure can support 45,000 pounds of vertical load on it without buckling or bending. So then the trick is finding a really powerful motor that is capable of actually using a gear system to kind of drive that tape measure essentially out in a straight fashion. And so what that allows you to do, because we want to lift the load about 20 inches up in the air, but our device has to be less than 12 inches, it allows us to actually coil up the lifting device itself, and then as we extend it, we force it into a straight shape that can then support the load.
So what sort of materials are you using for this? Because you mentioned the weight constraints and that this has to be a very light device.
Definitely. So weight has been a huge factor. Everything we look at, we have to say, oh my gosh, how much does that weigh? Nope, we can't use that. We can't use that. So what we've been looking at is the lightest weight steels we can find. We did look into titanium and aluminum, but frankly, aluminum isn't strong enough and titanium isn't stiff enough. So steel is kind of our only option, and we're afraid that it may put us over the 30-pound weight requirement for the competition, which is just something we're going to have to live with, because at the end of the day, what's really important is lifting the load, and if it means that the soldiers have to carry a few extra pounds in their backpack, then I think that's a trade-off they're willing to make. But steel really is what we're looking at. It's a 4,000 series steel, which is used in a lot of high-strength machine applications, gears, some aircraft applications, and then we're also looking at using a little bit of titanium for some of our gear mechanism, and that would be kind of your standard alpha titanium, which is really, really light and pretty darn strong.
You got the whole tape measure idea. Is that where the idea started, or was that kind of like an evolution of several discoveries along the way?
It definitely was an evolution. The first idea that we had looked nothing like this. We looked at airbags for a while. We looked at some kind of more complex systems. We thought we were going to use a piston or hydraulics, and we just started realizing that none of those systems would really work. They were going to be way too heavy, or they just weren't going to be strong enough, or we didn't have the knowledge to make them work. So actually it came down to we needed a design to bring to our instructor on Thursday. And we all sat down on Wednesday and said, guys, none of the designs that we have work. And so Wednesday night, I didn't sleep, and I brainstormed, and I prototyped with Legos. I mentioned earlier I like to play with Legos. I busted out the Legos, made a prototype. By Thursday, I had a design, presented it to the team. We modified it a little bit, and we've been going strong with it ever since. I don't want to say that we did it at the last minute, because there was a lot of thought that went into it before that point, but the design we have right now really was a last minute decision.
So how many people are on your team?
There are 5 of us, and I'm the project manager, but that doesn't mean I'm the team leader. I'm just kind of make sure that the project stays on track where it needs to be. Everyone is really supposed to come along, do an equal share of the project. So all of us are mechanical engineers. We all graduate in May. We all have a lot of experience under our belts, and so I think we can probably make something pretty cool.
And so is there like a presentation where everyone kind of shares their solution to this problem and
a public unveiling?
Oh, right. Okay, so the competition, they're going to hold it at, I don't remember the exact name of the Air Force Base, maybe Bradley Air Force Base, which is in Tennessee. So that's where they're going to actually hold the competition. So everyone's going to have to travel down there. They're going to have a number of actual U.S. Air Force parajumpers that'll use the device. And you'll get ranked on usability. You'll get ranked on creativity. You'll get ranked on how well you meet the objectives. And then every team also gives a presentation. And then the Air Force picks the one that they think will win. Now, just because you win, that doesn't mean the Air Force is actually going to use your device, but the team that won the competition last year, which was for a totally separate problem, they actually went on to start a company based on their device because the Air Force liked it so much. So they're definitely going strong, and I could see the winning device from this competition also spinning off a company if they so desired.
So if you win, are you going to start your own company, you think?
That's a really good question, and we've actually talked about it as a team. We've said, oh, what if we actually win? Do we want to do this for a living? In general, the response is no. Some of us have jobs lined up already. I'd like to go to graduate school. One of the team members is actually going into the military. He's going into active duty. So I think the team's going to kind of go their separate ways after this competition. But whether we win or lose, I think we're all going to have a lot of fun with it and definitely learn something.
All right. So obviously, in a tape measure type device, like the repeated stress on like a small area would be kind of like I don't want to say like a weak point, but a point at which it might pose a problem for lifting a big object. How does that really help? How do you kind of correct that?
You're saying the stress?
Yeah. How does like a small area take the stress of like a 45,000 pound?
Right. That was the biggest concern. One of our biggest concerns at first with this design was, well, can we actually make basically a post that will support this load? So we went through a whole bunch of different geometries, and if you've taken any engineering, you know that you have a few things you need to worry about when you have a post. You have to worry about both it failing just because it's not strong enough, it'll just get crushed. You also have to deal with buckling, which is a totally separate failure type. You've seen things buckle, they bend in the middle. So basically what we had to do was optimize our design so that it had the most cross-sectional area possible so that it wouldn't just get crushed, and then also had the highest moment of inertia possible so that it wouldn't buckle, because moment of inertia is extremely important when you're looking at buckling failure. In addition, I mentioned stiffness. Titanium, we couldn't use it because it wasn't stiff enough, and stiffness also contributes a lot to buckling, because the longer your post gets, the higher your risk of buckling. So it really was some of the most analytical design work went right into designing like what the cross section of that post will actually look like. So it looks like essentially like a C shape. So like I said, like a tape measure, it's kind of curved, but we took that to an extreme, and it's really like three sides of a box essentially.
Okay. And for our listeners who may not be very knowledgeable in mechanical engineering matters, exactly what is buckling? How does that occur? And you talked about moment of inertia as well.
Right. So buckling, so if you've ever seen a metal ruler and you try to kind of grab it at both ends and crush it vertically, it's going to bend in one direction. You're not actually going to crush the ruler. It'll just kind of flex out to one side. That's essentially what buckling is. What buckling is that gets so severe that the material can't take it and it actually permanently deforms. And then that's essentially catastrophic. It's a runaway failure. So the more it buckles, the more it wants to buckle, so the worse it gets. So you really, really have to avoid buckling, and it's a huge concern across all types of engineering, everything from biomedical, like orthopedic implants and things like that, all the way up to bridges and buildings. So buckling is really a huge failure mode that we had to think about a lot. Moment of inertia is essentially how much your shape resists buckling. So if you've ever seen a building that's under construction, it's made of I-beams. So if you cut that and look at the end of it, it looks like an eye. That is the best shape you can possibly get to resist buckling and still retain strength. So we definitely looked at an I-beam shape, but in the end, the C worked a lot better for us because it's a better compromise for the different things that we had to try to do.
And so exactly how does an I shape compare to a C shape in how it resists? Is there a better shape, or because I know you mentioned that the C was better for your project, but kind of compare and contrast the two for us.
Yeah, well, so like a C shape cross section, a C-channel beam, they are common in steel construction as well as I-beams are. But basically, if you imagine a C-channel, it's half of an I-beam. So if you take two C's and put them back to back, you essentially have an I. So a C is about half as good as an I if you think of it that way. But what our challenge was we needed a way to actually take that column and lift it up in the air. And so what we needed to do is we needed to put gear teeth along the side, and we needed to run it like a gear. So we needed to put a gear tooth on it, and then we also need to keep it as small as possible because the whole device has to be very small. So with that being said, we said we need to get rid of half of this I-beam and just make it a C-channel. Now, probably my civil engineering professors for the classes that I had when they taught about moment of inertia would kill me and say, you just really need to do I-beams because they're so much better in every way. And I would say they really are. But for this project, we have additional constraints that strength isn't the only thing we need to look at. We need to worry about how are we going to lift this post. So C-channels really not as good as I-beams, but I think they're the best solution for our project.
Right. And so this is this is designed for like continuous use. It's not like a one-time use and then it's done.
Right.
So like as an engineer, what precautions do you have to look at to make sure that this device is able to run time after time after time? Maybe they might take this out for like 2 weeks without ever having like any kind of like repair.
Right. That's a great thing that we had to take into account, and our instructors were really good at making sure that we kind of took those sort of things into account. One of our instructors is a reliability expert, so he was all about that. He said make sure it's reusable, make sure it's safe. So what we did, because the current solution, it's an airbag, once you use that air up, you're done. You can't get compressed air easily out in the field. So we said we want to be able to use it more than once. We want to be able to use it 4 or 5 times at least. So we were running it off of a battery, and we can recharge that battery anytime you get to a wall outlet, which, I mean, wall outlets aren't super common in the field either, but hopefully they're more common than a compressor. So we can run our device 4 or 5 times before it has to be recharged. And then in addition, if it gets damaged, we designed it to be use as many standard fasteners as possible. So Phillips screwdriver should be able to take apart much of the device. So if something breaks, if you have a spare one, you can swap parts. If you have any spare parts, you can swap them in and out. So basically what they call that in our classes and in mechanical engineering is design for reliability, design for manufacturability, design for repairability, and design for reusability. We tried to hit all 4 of those. So it's designed to be easy to make and then easy to swap out parts if you need to.
And when you look at, as you said, not manufacturability, it was, reusability.
Mm-hmm.
How much of or just between all those 4 types, how much of the design process is spent on each one? Like time-wise?
Yeah.
Which one's the hardest?
Yeah, so it's interesting because most of those, while they're all certainly very important, they all kind of have to follow the design that you use. So you got to come up with a design first, and then you try to optimize that design for, reusability and manufacturability. So I would say all in all, those aren't more than 20% of the amount of time we spend on this design. Most of it is really coming up with how will this design actually work. And then you say, oh, we need a pin to connect these 2 parts. Then your manufacturability or your repairability kicks in and you say, well, let's make that pin a screw that you can unscrew with a basic screwdriver. Because we have a lot of different options. We could try to do something a little more exotic that maybe would be a little stronger. But like I said, that's when you say, well, this is going to be in use. We want to be able to repair it. So let's swap it out for some standard components.
So have you tested your device yet? Is that, or kind of what point in the design process are you at currently?
So we're right in the midst of actually building the device itself. So we have a lot of the components all kind of assembled. We have the motor ready. We have our circuit that kind of drives the entire thing set up. We have the designs. We've done 3D modeling and made the gear and what the actual links of this flexible post are going to look like. And we've actually used the 3D printing lab right here on CSU's campus to prototype a lot of those parts and make sure that they work the way we expect them to. As far as actually making them out of steel, we haven't gotten to that stage yet because we have a limited budget for the project and we don't want to rush and buy things before we're sure what we're doing. So that's all happening in the next month. We're actually buying the parts, we're manufacturing them, and we're assembling them all together. But we have our driving circuit that kind of runs the whole thing, and we know that's all set up to work. And essentially we're trying to prepare as much as we can so that as soon as we get these physical parts that cost money, we're ready to do all the rest of the analysis, the testing, kind of the packaging, everything up to make it a really nice device.
So how does the motor work? What sort of materials did you use or that you're thinking of using currently to build that?
So the motor design is really, really complicated, and so we wanted to leave that to the experts. So we essentially picked the best. We decided what kind of specs we needed out of it. So how much torque do we need? How much output speed do we need? And what kind of reliability do we need from it? How often is it going to have to be running? And then the size and weight. And based on those, we actually just picked an off-the-shelf motor and purchased it. It was the best in terms of cost. It was the best in terms of time. Basically, in engineering, unless you're a motor designer, you just want to stay away from making motors because they'll cause you a lot of extra headache. So you just buy one and use it.
So which one did you choose based on all of those criteria that you were kind of looking for?
So the motor that we chose is manufactured by a company that's called Bodine. It spins at 2,000 RPM. It puts out 1 Newton meter of torque, which is, if you know anything about torque, that's pretty good for a motor of its size. It's about 7 inches long and about 4 inches in diameter, and it unfortunately weighs about 16 pounds, which, if you remember, it has to weigh, the whole device has to weigh under 30 pounds. So that's one of our really big ticket weight items that we're trying to get a lighter version if we can. But it was really important that we actually buy a motor as soon as possible because they take a few weeks to come in once you order them. So we went ahead and ordered one that we knew was a little too heavy and that we're going to have to use if nothing better comes along. But yeah, it's heavier than we would like, but it'll do its job.
So how does that weight compare to the beams that you're using in the gear set?
So the beam itself weighs about 12 pounds is what we're looking at. Okay. Based on the designs that we have. So you add that up, you're already really close to your 30 pounds, and you don't even have a battery or a motor or a base plate to connect everything together. So like I said, weight's just been a huge concern in this project. And then one thing that we need in between the motor and our post is we need a gearbox to slow down that motor. It spins at 2,000 RPM, and that's far too fast to actually lift our load. So the gearbox has actually been one of the most challenging things to decide what we're going to do for it because it's so heavy. Most gearboxes that can actually do what we want weigh actually about 50 pounds. And that was something that kind of surprised us because we didn't realize everything there was to know about gearboxes. And we said, oh yeah, we'll find a gearbox. It'll be small enough and it'll be light enough and it'll do everything we need it to. Well, not necessarily. There's some custom ones that we could get designed that would cost about $5,000, which is far outside our budget just by itself, that might be able to do it and might fit within the size that we need. But currently we're looking at possibly having to compromise some of the results of our device, like how much it can lift, because we need to buy a gearbox that's going to be, small enough and light enough. So, yeah, weight is just a huge trade-off for everything that we look at in this device, and the kind of the post that actually holds the device up and the motor and the gearbox by themselves already threaten to put us over the weight of 30 pounds.
So what exactly is your guys' budget for this project, and how have you has that been a big problem for you guys?
It's been a problem in that we can't do whatever we want. It's a pretty decent budget. Basically, the Air Force gave CSU $10,000 to actually perform the project, but because I said there are 2 teams competing at CSU, they split that in half. Okay. So we got $5,000. Then they put aside $2,000 for travel for the winning team to actually go to Tennessee and attend the competition. So $10,000 minus 2 for travel, it's 8. Cut it in half, you get $4,000 for your project, which is a little bit less than some of the other senior design teams have for their projects, but it's also it's about middle of the pack. $4,000 isn't enough, like I said, to do whatever we want, but it's enough that we can say we're willing to spend a little extra on this motor, or willing to spend a little extra on this material, or to have this device tested professionally so that we can make sure it works. So we've spent about a quarter of our budget at this point, and like I said, we're waiting on to actually pick some of our materials to buy them, and those are going to run a significant portion of the remaining budget. But I think we're ultimately going to come in under budget, but possibly with a device that doesn't do everything we need to. So that's just how life is. You got to make trade-offs.
Well, that's a lot of trade-offs, though. That's like, but it's like money versus it needing to do what you want it to do, versus, you know, an item that already might be overweight, trying to get it what you want it to do,
Mm-hmm.
versus, that's difficult.
It really is. And at the same time, you want to make sure that you have a device that reflects well in your team, so that you get a good grade in the class. And you want a device that actually works well, so that that's useful for the Air Force to use. So the number of different kind of requirements and goals that we're trying to balance is kind of staggering, and it's one of the most open-ended design projects that's in mechanical engineering this year. There are a lot of other projects that have really well-defined goals, and they say make sure you do X, Y, and Z, and you're completely good. The number of people we have to report to, the number of things that we want to actually try to achieve, it's been really challenging, actually, but I've enjoyed it.
And so, are you ever afraid, having such a kind of limited budget, that you're going to pick the material to make your stuff out of, and it's not going to perform like you imagined?
Oh, definitely. That's something that it keeps me awake in bed at night. Oh my gosh, I just ordered that motor for $300. Is it going to work? So we just have to make sure that we have testing procedures in place. And when you order a part, you have to tell that manufacturer, look, if this doesn't meet what you say it's going to meet, then I'm going to need a refund, or I'm going to need you to send another block of metal over, basically. So it's things that you wouldn't think about, because engineering, it's a lot different from hard science, because there's so much more interaction with people and so much more interaction with kind of reality. Science is great, and I love experimentation. I've performed research in the past, and it's a lot of fun. But at the end of the day, if you want something that's actually going to perform in the real world, there are a whole bunch of other things you have to think about, like testing, and what if this doesn't, budget, what if this doesn't meet my requirements that I needed to. So it's very different from just hard science.
And so how life and death is going to be the choice of the materials you're picking for the gears and the teeth and the shaft and the pull?
I wouldn't say it's life and death, because if we pick the wrong material, essentially our device isn't going to be as strong as we want it to. So that'll just make us lose more points when we go to competition, because they'll say, oh, look, we can only lift 35,000 instead of 45,000 pounds. That's because we picked the wrong material. And they'll say, okay, minus 10 points or whatever, and we just have to live with it. But as long as we can get something on time and actually manufacture it, then I think we're going to be okay, and we'll have something that works, or at least moves.
Right. And as a mechanical engineer, it's really easy to manufacture something that you yourself can use. But when you're manufacturing something and designing something intended for use with people who are not mechanical engineer superstars, how do you design with them in mind?
That is a huge concern that we've had, because we build this device, and it's like when you do anything yourself, when you're an expert in the field. I mean, not that I'm an expert, but when you know more about it than most people do, you understand it so well that you fail to see some things that might be obvious, or you see things that other people can't see, like how to actually use the device. So that's why it's been really nice that one of the members of our team is actually in the military, because he always brings us down to earth, and he says, look, guys, no one cares about this feature of your device. People are getting shot at. They want this device to work. They want it to work quickly, and they want it to be easy to use. So, so he's shot down a few of our ideas, and we gladly let him do that, because he's the one with the most real-world experience that's actually applicable to how this will be used.
Seems like that'd be a great asset to have, someone who's actually going to go out into the field and use this.
Yeah, it really is. And that's one of our kind of trump cards that we have against the other team, because we want CSU to be well represented, and we want every team to do well, but of course we want to go to competition, so we want to beat the other team. So the fact that we have him on our team is really good. He's even going to potentially get us access to some military vehicles, so that we can test our device on actual military vehicles.
So, do you have like a lot of contact with the other team? Do you talk with them about what they're doing, or?
We have kind of a interesting relationship. I don't know. A lot of us mechanical engineers are pretty well knit in our year, so like I know the project manager, the other team, a lot of our team members know each other. Two of our team members are actually one of my team members and one of the other team's members are roommates. So they just kind of have to keep their stuff to themselves, go in their own room and work on their project. But at this point, our designs are so drastically different that we just kind of want to both see the other one succeed. Because there's not as much direct competition. Yes, only one of us will be going to the competition ultimately, but we just want to see everyone do good work, and we want to send a good device to the competition in the end. So,
Final remarks?
Well, so kind of as a closing question here, you mentioned that you wanted to go to grad school after all of this. What's your dream job? What kind of career would you like in this particular field?
I would love to go work in robotics. So I mentioned we built some circuitry for this device. I loved building the circuit, kind of where programming and mechanical engineering come together is with robotics. So there are a lot of good robotics programs around the country, but after I would get my graduate degree, I'd love to go work at a company such as Boston Dynamics, which has been recently bought by Google. So maybe instead I'd rather go work at Google. But Boston Dynamics, if you've ever seen the Big Dog, it's a pretty cool robot that actually kind of looks like a pack mule, and they're trying to use it in the military to actually carry stuff around instead of actual live pack mules. So things like that are extremely complicated mechanical and software projects, and I would love to work on something like that.
So then would you like to continue to help the military specifically, or?
Military is a really cool application, and like I've seen in this design challenge, there are a lot of really interesting problems that you have to face that you just don't see anywhere else. Because military is just so much more demanding than a lot of like domestic applications. So if I worked on military projects for the rest of my life, I think I'd probably be happy because they'd be so interesting to me.
All right. Well, thank you, Adam, for coming in and talking to us today.
Yeah, thanks so much for having me on.
Project.